Well, g'day flatties and globe defenders. This is Critical Think from Down Under. Today we're going to talk about weight change versus latitude, which is empirical evidence that confirms we live on a rotating spheroid, which is why the flatties just hate it. Now, why is this experiment so fabulous? And it's because the results are sort of unexpected. Not many people expect that when you move your scales that a weight will weigh something different. So it's not really well known, but it's reasonably well known within the right circles. Now it's a non-optical observation, which means no refraction is required. Or maybe even the question comes up, do you have any observations that are not optical? Yes, we do. Yes, there's this one. And also there's no flat earth explanation for the naturally observed phenomenon. And no excuse available yet from the flat earth list of catchphrases. It's observable, testable, repeatable and falsifiable. Anyone can do the experiment, even flat earthers. And even Mr. Thrive and Survive has had a half-hearted attempt at it, but he didn't do the proper analysis. Anyway, the other thing is, if there was no R, it would not work. And if there was no rotation, it would not work. The results would be completely different. So I'm just going to pick out a couple of comments. I mean, I've got so much material here, but I'm going to have to break that off into a different video. But just for some introduction, we've got here... So first off, people, when they hear about this experiment, this is one of the comments I get. Oh, have you got any video proof, or should we just take your word for it? Well, yes, indeed. As the plain truth correctly points out, yes, I have got video proof. And here's another one. Never heard from that bloke again. Don't know why. And Brandon Toy, he says, this comment's funny. Maybe we can design an experiment to figure out why there are these weight differences. Duh. How about this experiment? Let's take some scales and weigh things at different latitudes and see if it correlates to the WGS84 model. What about that experiment? And then Brandon's also, cool, I'm glad you got a nice set of measurements / observations. Now, how are we going to figure out what caused the weight differences? Again, we do an analysis and we plot the correlation. It either correlates or it doesn't correlate. That's how we figure it out. And here get this, attempts to tell us what the scientific method is, and this is trying to find loopholes in the scientific method. So rather than examine the evidence, which is clearly pointing to a rotating spheroid, then there's the attempt to introduce the technicality and try and argue their way out of the measurement. Rather than just look at what's done, look at the analysis and try to understand it. But no, they don't want to accept it. And in Bob's latest video, we got a whole bunch of excuses. We get air pressure, humidity, temperature, etc., etc., etc. But I'm going to deal with all of those today. Every single one of those objections. I would like to point out that I've already dealt with the magnetism objection. I did a video, and I'll put a link in the description, where I introduced a magnetic field and showed that there was no difference to the weight. So there's one of those objections gone, and I've got more material from this latest measurement to refute that. So let's have a look at the experiment. First of all, we'll check out the equipment. Now I've got two sets of scales here. Yes, two sets of scales. Some of you may recall that in my last trip to Thailand in early 2020, my set of scales was mistaken for a Tonka toy by a young person, and it didn't quite work the same since. So I got a new set of scales, and that one is on the right, the new one, and the one on the left is the old one. Now the one on the left, I put one dot on it so I could distinguish it, and the one on the right has two dots. Now I wanted to use both these scales because, as I said, I didn't think that scales on the left was working properly anymore, and I wanted to compare the two on my trip and see what happened. I've also got this pocket scale. Now I thought, if this pocket scale, it's an El Cheapo pocket scale, if it could work reliably enough, you could stick it in your hand luggage and do a measurement with a little weight there, anywhere you like. But we'll see what happens with that. Now I've got my thermometer, a infrared thermometer I took with me to measure the temperature at each location. Now I've taken measurements at temperature, magnetic field, pressure, and GPS position and elevation. I did try to get accelerometer readings, but I found they're too unreliable, so I didn't include those. Now here's the method. I level the scales. They have adjustable feet and a bubble indicator of level. Weigh 500 grams on each scale, including the portable one. Swap the weights on scales 1 and 2, and then weigh 2 500-gram weights on the one scale on scale 1 and scale 2, because scale 3 only went to 500. Take my environment readings, and I've recorded all readings in here. Now, here is where I travelled. I travelled from Redcliffe down there in southern Queensland, and I drove up the coast all the way eventually to Cape Tribulation, which is about as far north as I could reasonably go. I took a little bit of a holiday in Palm Cove for a few days and travelled around a bit while I was there. Now here are the measurements. I took quite a few, over 20 measurements. I'm not going to show them all, but just so that the flatties can't declare that I made this up or I'm lying or anything, I've got a sample of my measurements here, and you can see that I actually went to these places, all different places, and did measurements, and they're all documented here. I've got the rest of them if somebody really wants to see them, but there we go. That was quite a good selection. Now we'll look at the results. I've put all these results into a spreadsheet, and I've got some calculations built into the spreadsheet. I've transferred some of my calculations from my Python program that I've got to analyse the data. Now, some of the geoid properties are up the top there. I use some of those in the calculations. I've got all my locations here, my latitude as measured, my elevation as measured, temperature as measured, pressure as measured, magnetic field as measured, humidity is not measured. I didn't have something to measure it, but I've looked up all the meteorological graphs for these particular reasons, and it's fairly consistent, and these are the best guess for humidity. And this is to calculate density of the air, because the flat earthers like to think that weight is a property of density. So I've got that density calculation, and we'll use that. So then I've got all my readings here, the first scale, second scale, third scale at 500 grams, and 1,000 grams on scale 1 and scale 2. This other column here is a raw WGS 84 calculation, and then there's a rotating sphere calculation, flat earth calculation based on density. I'll try to explain how that was arrived with this. Now, with the WGS 84 calculation, I have to match the calibration of the calculation to the calibration of the scales, and the way I do that is by a least squares method. There's another column over here which measures the change in weight that should happen if you calculate it correctly by the buoyancy formula. Now, of course, the amount of air displaced by the weight will have an effect, and as the density of the air changes, this will alter the weight by a little bit. Not as much as flat earthers would like, so I've put that figure in here, and using each weight is about 62 cc's, and that works out the buoyancy for 1,000 grams is not measurable in these circumstances. So I plotted a few things down the bottom here just to illustrate when things are correlated and when things are not. For example, we've got air pressure versus altitude. This is a good correlation. It's a straight line, and we know that air pressure and altitude are directly related, and that's why that's a straight line. And we've got air temperature versus altitude. But as you can see, we can have a bunch of air temperatures at the same altitude, like sea level, so it's not really a relationship there, but we also do know that as you get higher, the temperature gets lower, and this is sort of indicated on this graph. And then we have weight versus magnetic field. Remember, the flatties like to think that the magnetic field will affect the weight, and it's all over the shop there. It's not really a thing, but if somebody wanted to set up an experiment, they could do that. Remember, I've already tested this, and I couldn't make the weight change by changing the magnetic field. So here's the Earth's magnetic field. This sort of suggests it's a bit random, and there's no straight line there. Then we've got weight versus air pressure, and this would be air pressure loosely relates to density, but as you can see again, we've got a whole bunch of different weights at the same air pressure. So, that's not a correlation. You can't say that air pressure caused these differences in weight that we observed here because of this graph. And again, weight versus altitude. Now, there is a relationship between weight and altitude, and I'll show that on the graph. But this one here, so we can get at the same altitude, well, mostly near sea level, we can get many different weights. So that's not the relationship that explains what we've observed with this weight change versus latitude. And then again, weight versus air temperature. You could interpret this as having a slight downward trend. And yeah, that arises because as you go further north, the temperature tends to get a bit hotter, and also the weight does go down for other reasons. But as you can see here, there's no direct relationship between weight and air temperature. And over here we've got weight versus density. So I've plotted the weight measured against the air density, and as you can see, there's no direct correlation. But if you wanted to draw a trend line through there, and I have taken that as a trend line to try and work out some kind of prediction against density. Now, this is not valid because this is not a strong enough relationship, but it's the best we got. Let's say if we were a flat earther, we could measure weight versus density, establish this trend line, and then use it in a calculation. So that's what I've done to try and get a flat earth density weight change graph. So now we look at what we've got over here, plotted over here, everything versus latitude. Now remember what we said, weight versus latitude matches the rotating spheroid WGS 84. Now this particular plot, I'll change a few things here. Now the first we've got here is scale 1 and scale 2 with the 500 grams on them. Now remember I said scale 1 was suspected to be broken, and this is illustrated on this graph. As you can see, scale 2 follows this grey line. Scale 1 has these dips in it that don't correspond at scale 2. So every now and then the broken scale gives us a strange reading, so maybe it's got a dry joint or a cracked circuit board there somewhere. Now we'll change this and we'll introduce the scale 3, which is the El Cheapo scale. I was hoping could use it, but then again it suffers from some erratic readings. But if you were going to use it over long distances, you could still use this scale to demonstrate weight change versus latitude, but it's not so good on the fine-grained close latitudes. But as you can see, over a long distance it does give a trend downwards. And now we'll look at the 1000 grams. And again, scale 1 has these dips every now and then. It has a bit of a fit and doesn't measure correctly. So we'll eliminate scale 1 and just take the data from scale 2. So that's the data from scale 2. Now you'll see on my data that there were 3 occasions where I've got readings at different heights at very similar latitudes. So I've got Rockhampton, it's just right next to Mount Archer. I've got readings at different heights. So Rockhampton about 22 metres above sea level, Mount Archer about 600. Then Townsville and Castle Hill here. There's a 270 metre elevation there. And then the other readings was Palm Cove and Curanda are very close in terms of latitude. And then there's a 300 metre difference. And this results in a dip in the weight, fairly consistent dip in the weight. So there's these here is Rockhampton and Townsville, which is this one 19 something, and Palm Cove and Curanda. So you can see there's a consistent dip as you get higher. Now let's look at how that compares with what's predicted with the WGS 84 model. And as you can see, this is a damn fine fit. Look at that. Even the dips predicted by the change in height, they come out there. Look at that. The shape of the curve matches. There's a few points that are off, especially this last one here at Cape Tribulation. I don't know what happened there. That was a difficult measurement, and who's to know if there's a gravitational anomaly or not. But this measurement is the odd man out. All the others are reasonably close. I also mentioned I calculated the flat Earth predicted weight based on relative density. So we'll add that one in, our flat density calculation. And as you can see, even if you try to do it by density, it doesn't look anything like the measurement. So no, flatties, out of luck there as well. Look how good the rotating sphere model fits. And look, no, sorry, density's not going to explain this variation in the weight. You're going to have to try some other excuse. Okay, now let's look at some of the other things plotted versus latitude. So we'll remove the scale there and let's go with pressure. Really, pressure seems to be not related to latitude. Okay, let's look at magnetic field. Oh, that doesn't seem to have much correlation either. And then let's look at temperature. And yes, there is a slight increase of temperature as we go further towards the tropics. Not so surprising really, is it? Now I do have another analysis method. I've got a Python program that accumulates data, and Bob the Science Guy has shown that graph on Research Flat Moon channel, and I'll show my results here now. Now this is my plot of my run up the Queensland coast and back again, and as you can see, it follows the WGS 84 line. Doesn't follow flat Earth, doesn't follow a non-rotating spheroid, and a spherical shape doesn't quite fit either. So a oblate spheroid rotating is the only shape that fits. Now here's the graph that I gave Bob and he showed on his video, and I've made a couple of refinements to this. First thing is I've averaged out these green dots on my first measurement. They're all taken at the same time at the same location. So I've averaged them out and I've replotted that. And this contains a couple more adjustments that were slightly incorrect before. And there's my new graph that aggregates everything. Now, each measurement was done at a different calibration, so the Python program attempts to line them all up to a standard calibration, which in this case 27 degrees latitude and at sea level. So it has to move the whole measurement series by up or down in weight to match 1,000 grams at sea level at 27 degrees, and that's how I compare them. So if I was to try and plot them all, it wouldn't mean anything because they'd all be different calibrations. And here I've done the same thing to try and fit a rotating sphere shaped rather than spheroid, and as you can see, there's a definite bias at the low end and the top end, so the rotating sphere is not good enough. It needs to be spheroid. And then I tried to fit it all to a flat Earth. As you can see, in all cases the similar coloured dots have a slope. They have a slope from here to here. These all angle down there, which shows that there is a relationship, and the flat Earth says there should be none. Not until you can come up with a calculation and a measurement anyway. And with all those aggregated results, and I run through all the least squares fit and the error analysis, with everybody's measurements lumped together, we've got the WGS model is a 98.4% fit. And flat Earth just doesn't fit at all. So you see, that's how we determine that it's rotation and centrifugal force and gravitation that causes this weight change versus latitude. It fits the prediction, whereas it does not fit the predictions for density, magnetic field, whatever else you want to make up and say, oh, there must be something, but you just don't know what it is, and unless you measure everything in the whole wide world, I'm not going to listen to your results. Yeah, that's right. So come up with something better, or you're going to have to accept this. So we'll leave you with these words of wisdom.
Goes on about the difference in the weight of things at the equator compared to other places in the Earth. Have you actually gone and measured it? Have you ever done it? We understand that in the model, based on the spin and centrifugals, centripetal, whatever forces, that's the result that you can calculate based on your model. But has anyone actually gone and measured this so-called difference? Has anyone actually measured that a kilogram weighed in the, somewhere up north is any different to a kilogram weighed on the equator? Has anyone actually gone and done that? No, they have not. A kilogram is a kilogram wherever you are on the Earth.